Jnanam Paramam Dhyayam. Knowledge is supreme.
Welcome back. So we are looking at advanced control, and before the break or in the first few videos of this week, we have looked at traditional advanced controllers. So we looked at simple modifications of control variable, one manipulated variable, PID controllers, and we saw how those can improve the performance of these PID controllers in real applications where objectives might be slightly different than having a single control variable and single manipulated input. Earlier these used to be called as advanced controllers because they were advancements over a single variable PID controllers. Nowadays the controllers which are used are really advanced in terms of the logic which is used in terms of taking the controlled variable to how it manipulates the manipulated variable, and those are really known as advanced controllers. So just to distinguish between the traditional advanced controllers which we use, these we will call as model based advanced control, because these will use some sort of a process model in order to improve the performance. If you go back to PID control, all the information it needs in terms of the process is that what is the direction or what is the gain between the controlled variable and the manipulated variable. As long as you know the gain is positive or negative, the PID controller can work. It does not need any other information about the process. Having said that, if we have information about the process, can we make use of that additional information and improve the performance of the PID control? That is the focus of this week, this portion of the week where we will be using this model based advanced control. So in terms of what are your objectives, we will see why there is a need for using process model in order to improve the performance of a process, and we will look at some of the advanced control, such model based advanced controllers, and you should be able to tell what is the main working principle behind these. We will not be able to go through the details of implementation or considering all the cases in such kind of a system. Each of these the advanced controllers which we are going to be looking, they are all areas of active research. A lot of books are written on them. So I am just going to give you a flavor or introduction to these advanced controllers, so that if you see such kind of controllers in any industry you are visiting or you are working, you should be able to identify that, and you would know what are the motivation or main components of that particular system. So all these controllers which we are going to see now, they are all model based. So what I mean by that is when you have a PID control logic, it does not depend on the actual process model. So it does. So when you have a process where your input is u and your output is y, you want to control your y by using u, and when you use a traditional PID sort of a control, and let us say this is your process model GP. So in order to design this PID control design does not need GP per se. You can always do trial and error, or a lot of the logic of this control depends only on the error. So it depends on what is my current value and what is the desired value, and the PID control law will either take a proportional action or a proportional integral action or proportional integral and derivative action. So it does not care whatever is the actual relationship between u and y. As long as you know this relationship has a positive effect or a negative effect in terms of gain, the controller would work fine. What we are now looking at in terms of model based control is, can we use this GP? So in model based control, use this GP to derive the control law. So, when you do that, it will be a model based control, because your control law is dependent on the model between the output and the input. So, what is the notion of this? So, for that let us look at how a control system looks like. So, typically you have this process model which is going from input to the output. So, GP tells me if I change my input, how does my Y change? In terms of control, it is exactly the opposite. In control, the input to the controller, let us say a PID controller or a model based controller, the input for the controller is the output of the process. So, if you look at the control system, your input is Y and the output of a control system is the manipulated input. So, it is exactly the reverse map of your process. In terms of a best control, so what I want from a controller is, I want to make sure my Y is equal to the set value. So, what I want is, I want my Y to take a desired value. So, can I do this by simply saying if I go from U to Y and I use GP, now I want to solve the reverse problem. I want Y to be equal to Y set and I want to know what U should I use. So, that is same as inverting this model. So, if I take GP inverse, it is going to tell me what form my U should take in order to have a value of Y set. So, that is why when you say a model based control, it is the control law which is going to use GP inverse. So, even though I said it uses this model, it actually uses the inverse of the model, because controller model is the ideal controller model is the inverse of a process model. You want to move from Y to U and the process model is from U to Y. So, when you use such kind of a control law which is dependent on, let us say, an inverse of a process, that will be a model based control. So, you can see that this control law will not be universal like a PID control law, which takes error, multiplies it by some gain Kc or takes its integral and multiplies it by Kc by tau, Kc over tau y. So, that is a universal control law. Here the control law will be dependent on the form of GP, and that is why it is a tailor made control law, and as you are using process information, you will see that the performance will be much better in most of the cases than a PID controller. So, there are many such model based advanced control strategies. We will be focusing only on two of those strategies. The reason I am selecting those are because they are very popularly, they are very popular in terms of advanced model based advanced control, and both of them have been commercialized, and there are a lot of industrial application or industrial implementations of both these advanced controllers. So, we will be focusing specifically on these two control strategies. One is an internal model controller known as an IMC, and the other one will be dynamic matrix control or DMC, and which eventually gets the current form of in the current form it has been improved to what is known as a model predictive control or MPC. So, let us start with IMC or internal model control, and its root lies with what is known as an open loop control. So, when we talk about model based control, the first or the simplest way it can be implemented is open loop control. Now, if you want to contrast it with PID control is a closed loop control. You had a very nice closed loop between the controlled variable and manipulated input. Here you will see that that is no longer required when you want to do a simple model based controller. So, let us say this is your process which goes from U to Y, and I want to look at the servo performance of this or servo control. So, I want my y to go to a value of y set. So, what I can do is I have this y set, I can pass it through GP inverse. So, whatever is the u required, I will just give it to the process. Let us see what this system does. So, now we are interested in is, so again let us say we are working in the Laplace domain. So, if you want to write your transfer function between y s and y set s, it is the multiplication of this and this. So, you can see that y s is, so y s is equal to u times g p. So, u s into g p s over y set s, and u s itself is equal to g p inverse times y set s. So, g p inverse s, g p s, y set s and y set s get cancelled. So, this is equal to 1. So, you can see that if the transfer function between y and y set is 1, what it means is if I give a step change in y set, then my y is going to exactly follow y set. Even though I am drawing it slightly differently, what I mean is they exactly follow each other. So, this is y. So, you have achieved your servo control, that you have moved your y from current value to new y set, and you can see that this is an instantaneous control. This was not possible in the PID control. In PID control, even though you gave a set point step change in y set, your actual output would take some time to go from the current value to the final desired value by depending on what are your controller parameters. So, you can see that this is much better than your traditional PID controller, simply because you are using the process information. You exactly know how your system is going to respond, or what is the exact input which is going to give me the desired output. So, if it is such a cool strategy, why do not we use it? Because there are certain limitations in terms of practical implementation. So, first and foremost is, here we are using the knowledge that GP is known. So, what are the limitations of this? So, first and foremost is GP is known exactly. If GP is known exactly, you can have GP inverse to be known exactly, and then you can take a perfect control and get an instantaneous control. Now, when you talk about a real process, real industrial system, hardly you will have a model about the process, or there is no such model which can capture the reality. So, in that case, your whatever GP or the process model you have is sort of an approximation of the actual behavior. So, because of that you would never have a perfect model. So, perfect model is not available. So, here GP is required to be known exactly. So, perfect model is required, which is typically not possible, and what you end up with having is known as a plant model mismatch. So, if that is the case, your open loop control will not work, because it will assume that the process is going to take a certain it is going to follow a certain relationship, but in reality the actual system does not follow that relationship. So, because of this plant model mismatch, you will never reach the set point, and that is one of the major reasons why a feedback control is needed or why feedback is required. So, when we talked about feedback control and its robustness, the main reason comes from the fact that unless you have a feedback from a system, you do not know whether you are taking a correct action or not. So, open loop control, because of lack of feedback, would never be able to counter plant model mismatch. The second limitation is GP may not be invertible. I said that your control law is GP inverse times Y. So, that assumes that GP inverse exists. Now, let us take an example that you have a first order plus dead time process. First order plus dead time process. So, that your GP is Kp over tau s plus 1 e raised to minus TdS. When I say GP inverse, what would I get? Tau s plus 1 over Kp into e raised to power TdS. So, you can see that now you have a positive delay or positive dead time. What does that mean? That means I want to take an action Td times before the current value. So, if you want to really work in terms of the time domain, so this is Us over Ys. So, what you are really going to get is, so this is tau over Kp. S is generally the derivative. So, you will have dy over dt plus 1 over Kp times y. So, this is the inverse of this particular piece, and then as you have e raised to power TdS, the values of y and the derivative I want is at t plus Td. So, in order to compute the output, the manipulated input at the current instant, what I want is the derivative of the output at a future time and also the value of output at the future time. So, if as the process has not reached that particular future time, there is no way I can use this information and calculate the manipulated variable. So, this is practically infeasible. Which is true, because what this FOPDT or first order plus dead time model tells me is that when I make a certain input move, unless a time of Td is spent, the output is not going to show any effect. So, if that is true, then I cannot have my output follow the set point exactly or instantaneously. You have to wait for a certain time before your system can respond to the input. So, there is no way you can make your system instantaneous or let this dead time go away by having a model based control. So, physically that is the interpretation that you cannot have an instantaneous control when you have a dead time in your system. In terms of mathematics, this is what you get, which says that mathematically also it is infeasible. Mathematically it is not infeasible. What I mean to say is, whatever mathematical form you get, it cannot be practically implemented, because you require future values of the process. So, this is one example that if you have a dead time, you cannot invert the model. Similarly, you can do analysis that if you have an inverse response or a 0 in the right half plane, again you cannot invert that particular model. So, that is the limitation of open loop control, that you may not have a process model which is invertible. So, in that case your system may not really give you the instantaneous control. Another limitation is that not exactly limitation, but in terms of implementation is that when you take an inverse of the transfer function, the transfer function which you get for controller may not be proper. So, GP inverse may not be proper. What I mean by proper is a proper transfer function is a transfer function where you have the order or the degree of the numerator is less than the degree of denominator, then it can be physically implemented. If you take GP as Kp over tau s plus 1, tau s plus 2, a single simple second order system, then GP inverse becomes 1 over Kp tau s plus 1, tau s plus 2. So, you can see that the numerator has tau square, but the denominator has 1. So, degree of numerator has s square as the degree of 2, but denominator has 1. So, no physical controller can give you a transfer function like this. So, that is why you cannot use directly a GP inverse. What you have to use is a filter. So, filter needs to be added, so that you make the order of denominator at least equal to the order of numerator. So, in this case what you would use is, so GC or the controller transfer function will be GP inverse times what we known as a filter, so that it will be GP inverse over lambda s plus 1 square, so that you will have s square in the numerator and s square in the denominator. So, this 1 over lambda s plus 1 is a filter, is a simple first order process, and by having a filter of higher order, you can make sure your controller transfer function is proper. So, in general the controller in the model based control, how you get it. So, you take your process transfer function. So, let us say GPS is the process transfer function, you break it up into whatever that is invertible part. So, you convert it into GP minus s multiplied by GP plus s, where GP minus s is the part which is invertible and GP plus s is the part which is non invertible, and then in terms of your control you invert the non invertible the invertible part. So, you take this and you simply add the filter. So, that becomes your controller, which here we will be referring as QS. So, you take only the part which is invertible, invert it and then add a filter to it. Now, we have seen there are some limitations, and mostly they come from the fact that there is no feedback in this open loop control, even if the another that also has a significant manifestation in terms of disturbances. If an unknown disturbance affects the system, there is no way this open loop control will be able to handle that. So, in order to get rid of to satisfy these avoid these limitations, get rid of these limitations, the practical implementation of this is known as an internal model control, or IMC. So, what we do in IMC, the principle or the motivation is that because of lack of feedback, your open loop control is not able to satisfy work in the case of plant model mismatch. So, you introduce feedback into the system. So, what you do is, let us say this is your process GP, which goes from u to y, and this GP is the actual process. You may have the transfer function for it, or you may not have transfer function for it, but you can have, what you can have is a representation of the process. So, let us say you have a model of the process, we will call it as GP tilde s. So, whenever you give some input to the process, you compute what would have been the output if this was the model of the process. So, this takes into account whether there is a difference in terms of the plant and the model which you are going to use for the control. It also takes care of if there was any disturbance which was affecting, which was not part of the model, and you take the difference between the two. So, you take this as positive and this as negative. So, you take the difference between the actual output and the predicted output, and then you use the feedback in terms of whatever is your set point, and then this is your model based controller QS, and it will give you the U. So, this is your controller. So, this was your open loop controller, the way we derived QS. The only difference is now you are also using the difference between actual value and the predicted value. As you are using this difference between Y and YP to drive this open loop controller, it will ensure that if there is any disturbance which is affecting the process, it will trigger the difference, between Y and YP, and then that will be rectified to the open loop control. So, you will see that by incorporating this sort of a feedback between actual value and the predicted value, you are still using the the model of the process in order to compute the control law, and this open loop controller also uses that. So, it is a model based control strategy. So, your overall controller, if you want to see, is this. So, all these actions are done inside a controller. So, this would be your IMC controller. It has two parts, one is prediction of the output and other is this control law. So, by having a desired value as well as the error between prediction and model, it will going to prediction and actual plant, it is going to compute the manipulated variable. In terms of the transfer function, if you compute it, you would realize that the corresponding transfer function can be given as Ys will be this Y set S, and this is the disturbance transfer function. So, it looks very much similar to your PID control law. So, if you see, try to recollect, this was your servo transfer function and this was your regulatory transfer function. The only difference now is it is in terms of QS, which is your model based controller, and it also incorporates this factor Gp minus Gp tilde S, which captures the plant model mismatch. So, if your model captures the plant accurately, which is not practically the case, but if that is possible, then this term would go away and your entire control law will be simply Gp QS over 1, and so the denominator will simply be 1 in that case. So, in terms of perfect model, what you require is in order, so the another advantage of this control strategy is that in order for this system to be stable, all you need is your process should be stable. As long as your process is stable, your controller remains stable. That was again not the case in terms of a PID control, which we saw that in the cases of dead times or more third order or higher order systems, there was a limitation in terms of controller parameters in order to ensure stability. So, these also are additional advantages in terms of going for IMC. How do we implement this IMC control? There are multiple ways in which this IMC control can be implemented. I will show you a simple way in which IMC controller can be implemented, that is by converting it the structure into an equivalent PID control. So, we can take the same structure which we had earlier. So, IMC implemented as PID. So, that way if you, so let me just show you what we have done. So, this is your process Gp, this gives you Y, you also have this Gp tilde S, which is the prediction. You take the difference between these two. then this is your set point, or let me call it y set, and then you have this controller qs which is going to give you u of s. So, now what I would do is, so this is y tilde s. So, we can simply rearrange this to be on the other side. So, instead of showing it here, I can just show it in this direction, does not make any difference, right. And now, what you have is this y tilde s is subtraction here, so this is plus and this is minus. So, there is one subtraction here and the second subtraction here. So, if I want to move this y tilde s directly here, I can simply add it to this particular portion. So, I can disconnect it from here, and if I put it here, then this is minus and minus plus. So, I can simply have a plus here. So, the same structure, if I simply rearrange it, what I get is a structure like this. So, can you notice something here? What we have done is, this is equivalent to IMC. So, as I showed earlier, this is still IMC. The only thing is I have rearranged the block diagram without changing the output, and what you are getting is, if you look at this, this is actually the controller transfer function which we were using earlier. So, you have a process transfer function, you have a y, you compare it with the set point, you get an error, and then your controller works on the error. So, this is same as a GC in the PID control. And in this case, this GCS is actually equal to QS over 1 minus QS GP tilde S. So, for IMC controller, this GC is this, and if I want to see that this IMC controller should have a form of a PID controller, I can simply equate it to Kc 1 plus 1 over tau I s plus tau d s, and if I compare these two, in order to get a realization of IMC controller in terms of PID, what you will get is you can simply compare these two, and it will give you the values of Kc, tau I and tau d for a particular process. So, here I am showing you that if you have a first order plus dead time process, then what you will get is, when you do this comparison, you will get Kc as this, tau I as this and tau d as this. So, what you are essentially doing is, if you use a PID controller with these values of the tuning parameters, then that PID controller will work as an IMC controller. And why is this is still a model based controller? Because if you see this, your Kc is dependent on tau, Td and Kp, which are model parameters. Your tau I is a function of tau, which is also a model parameter. So, it is still a model based control. The only thing is that you are implementing this IMC as a PID controller. So, that is one way of implementing IMC. I am not saying that is the only way IMC can be implemented. Obviously, when you are doing this, you are making certain assumptions about the process. So, the effectiveness of IMC might be limited a little bit, but the advantage you gain is that by using the same architecture of PID control, you can implement an advanced model based control using the same architecture. So, we will take a break here, and after the break we will move on to the second advanced control strategy, which is known as a dynamic matrix control. Thank you.